Welcome back to module 7 of the unit Determinants and Matrices, and we will continue with some examples on determinants in this module. Recall that in the previous module we have defined what is a determinant and how to compute the determinant of a square matrix and the various properties of determinants. So we will continue with some more examples on determinants. Let's say I have this. Find the value of the determinant 13, 16, 19, 14, 17, 20, 15, 18, 21. Okay. So we very well know that the procedure how to compute the determinant. So I have 13, 16, 19, 14, 17, 20, 15, 18, 21. Okay, so as we discussed in the previous module, what we do is we start with the first number here. Okay, so I have 13. I take out the respective column and the row. Okay, this is the remaining part. So 13 into the minor corresponding to that, that is 17, 20, 18, 21. Then I go to the next element. Then the sign changes, minus. I have 16 here. So corresponding to 16, the respective column and the row, if I take out, then I have 14, 20, 15, 21, 14, 20, 15, 21. That is this 14, 20, 15, 21. And then finally I go to the next number, the sign changes. So I have 19, the respective column and the respective row. In that case I have this, the minor corresponding to that is 14, 17, 15, 18, 15, 18. Okay, so I have to calculate this. So 13 into, so I have 17 into 21. So I have to multiply 17 to 21 and then minus 18 to 20. 17 to 21 is 357 minus 18 into 20, that is 360, minus 16 into 14 into 21, that is 294, minus 15 into 20, that is 300, plus 19 into 14 into 18 is 252, minus 15 into 17 is 255. Okay, so if I simplify this, I have 13 into 357 minus 360 is minus 3, minus 16 into 294 minus 300 is minus 6, plus 19 into 252 minus 255 is minus 3. Okay, so 13 minus 3 is minus 39, minus 16 into minus 6 is plus 96, and 19 into minus 3 is minus 57. Now what we'll see is that minus 39 minus 57 is minus 96, and I have plus 96 here, so they will cancel each other. I'll get the determinant as 0. Okay, so this is how we know we compute the determinant, and the value, the determinant of this matrix that we have considered here comes to equal to 0. Okay, now we have also very well studied the the properties of determinants, and sometimes we can we use properties of the determinants in simplifying or computing a respective determinant. Okay, like in this example itself, if I go by the properties, of course we have already found out that the determinant of this determinant is equal to 0. Okay, if I go by the properties, okay, and let us say this, I have R1 here, R2 here, R3 here, and then this is the column 1, column 2 and column 3. Okay. The last property that we have discussed in the previous module is that whatever arithmetic that we carry out between the corresponding elements of rows and columns, the value of the determinant remains the same. So let me replace R2 by R2 minus R1 here. Okay, so the determinant that I'll get is, so 13, 16, 19. I'm replacing, subtracting R1 from R2, and that I'm writing in place of R2. So 14 minus 13 is 1, 17 minus 16 is 1, 20 minus 19 is also 1. And at the same time, let me also look at R3. Let me replace this R3 by R3 minus R1. So I'm subtracting R1 from R3. So 15 minus 13 is 2. 18 minus 16 is 2. 21 minus 19 is also 2. So this determinant is equal to this determinant by carrying out this row transformations. Now what I can do is, here 2 is common in all the terms in the third row. So I'll take 2 out. I can 2 common. So I have 13, 16, 19, 1, 1, 1, and I'm taking 2 common from all these terms. What I get is 1, 1, 1. Now what you'll see is that this row and this row here both are identical, and one of the property of the determinant says that if there are 2 identical rows or columns, then the determinant is equal to 0. So I have this 2, so the value of this determinant is equal to 0. We get the value, this determinant equal to 0. Okay, so I could use these properties of determinants in finding the determinant, and this is much simpler as compared to what I did in the previous slide, where I manually found out the value of the determinant by the procedure we know. So this is how these properties can also be used in finding the value of a determinant. Let me go to this example. Solve the equation. So I have a determinant equation here. So I want to find out, so when I say I want to solve this equation, I precisely mean I want to find out the value of x. Okay, so we'll solve, we'll compute this determinant first, we'll simplify it. We know that this determinant is equal to x into, so I'm starting with x, so 5 into 12, that is 60, minus, I have 7 minus x multiplied to 8, so x, this, the minor corresponding to that is 5 into this minus 7 minus x into 8, minus 2 into, so I go to the next value, so it is now minus 2 here, the corresponding to 2, I have 3 into 12, that is 36, minus x plus 1 into 8, x plus 1 into 8, and then I go to the next element, so plus x plus 3, this multiplied with, so the corresponding row and column I've taken out, so 3 into 7 minus x, okay, this minus x plus 1 into 5, x plus 1 into 5, so I have this equal to 0. On the right side it is equal to 0. Okay, so I try to solve this, I try to simplify. So what I have is x into, I have 60 minus 7 into 8 is 56, minus x into 8 is minus 8x. Okay, so I have this minus 2 into 36 minus 8x, x into 8 is 8x, and 1 minus 1 into 8 is minus 8. Plus I have x plus 3, okay, into I have 21, 3 into 1, 3 into 7, 21, minus 3x, x into 5, 5x with a negative sign here, so minus 5x, and minus 1 into 5, minus 5, and this is equal to 0. So what I have is x into, I have 60 minus 56, minus into minus 8x is plus 8x, minus 2 into 36 minus 8 is 28, minus 8x, plus x plus 3 into, I have 21 minus 5, that is 16, and minus 3x minus 5x is minus 8x, that is equal to 0. Okay, so what I have is x into 60 minus 5x is 4, 60 minus 56 is 4, plus 8x, plus 2 into, so I'll multiply this 2 to 28, so I have 56, so minus 2 into 28 is minus 56, and minus 2 into minus 8x is plus 16x, plus I have x into 16, so I have 16x, and x into minus 8x is minus 8x square. I multiply 3 to 16, 3 into 16 is 48, and 3 into minus 8x is minus 24x, and this is equal to 0. So this of course I have this. So this implies, so I have x into 4, that is 4x, x into 8x is plus 8x square, minus 56 plus 16x plus 16x minus 8x square plus 48 minus 28, 4x equal to 0. So this 8x square minus 8x square will cancel. I have 4x plus 16x, that is 20x. Okay, this is 16x. So I have 4x, 16x, 16x, that is 32 and 4, 36x. 36x minus 24x is 12x. So I have 12x. I have minus 56 and plus 48, that is equal to minus 8, and this is equal to 0. And this will give me the value of x. So x will be equal to 8 upon 12, that is equal to 2 upon 3. Okay, so I have found out the value of x. I have solved this equation, and we saw that the value of x is equal to 2 upon 3. We'll go to the next example. Let us say I have this question. Show that this determinant is equal to 0. Okay, so I have this determinant here. So let me start with this determinant. 1x, x square minus yz. I have 1 y square minus zx. And I have 1 z square minus xy. Okay, so what I can do is I can simplify it as per how we solve a determinant. Okay, so what I'll do is I'll start with the first element. So it is 1 into, so it is, so we take out the respective row and the respective column. So I have 1 y multiplied to this. So y multiplied to z square minus xy minus z multiplied to this. So z into this, y square minus zx. Then I go to the next element. So I have then minus x into, take out the respective column, respective row. So now 1 multiplied to this, 1 multiplied to z square minus xy, and minus this 1 multiplied to this, 1 multiplied to y square minus zx. Then I go to the last element. So plus x square minus yz, this into the respective column, the respective row, 1 into z minus 1 into y, 1 into y. Okay, so I'll just simplify this. So I have y multiplied to z square minus y multiplied to xy. So y into y will be x square. So I have x into y square minus I have z into y square. So I have y square z minus z into minus zx. So that is plus I have x, and this z into z will be z square. So x into z square minus x into, here I have z square minus xy minus 1 into y square is y square, and minus of minus zx is plus zx. The same way, let me simplify this bracket as well. Plus I have x square into z, here x square into z, then x square into minus y, so that will be minus x square y, then minus yz multiplied to z, so I have minus y z into z, z square, and minus yz into minus y is minus y square z. Okay, you can see if we can cancel some terms here, like I have yz square here, this yz square you can cancel with minus yz square. Okay, and you have x any other term. I have x z square here, no. So y square z, I have minus y square z. Anyway, let us simplify further. So I have minus xy square minus y square z plus xz square. Now let me simplify this term. So x multiplied to z square, so minus xz square minus x multiplied to minus xy, so it will be plus x into x square into y. Next I have minus x into minus y square, so plus xy square, and then minus x multiplied to plus zx, that will give me minus x into x is x square into this z, okay, plus x square z minus x square y minus y square z. Okay, so minus, so you can just cancel out whatever terms you can cancel, like here minus xy square, okay, minus xy square I have, and I have a plus xy square, so this minus xy square you can cancel with plus y square. Then I have minus y square z, and you have plus y square z. No, I couldn't. So xz square here I have minus xz square, and this x square y I have minus x square y here. Then minus x square z is and I have plus x square z, and this term here I have minus x y square z, and I have minus y square z. Did I miss any sign here? Yes, here this minus yz and into minus y, this minus into minus is plus, so this is actually plus, so I have plus here, and that's how these two terms will cancel, and all the terms now we have cancelled, so I got the value as equal to 0. Okay, so this is how I do it. By using manually, by using how we actually compute a determinant. I could have also used properties of determinants in doing so. Like what I could have done is, like if I look at this R2 and R3, okay, let me look at let me replace R2 by R2 minus R1. In that case, what is the determinant that I'll get? I'll get 1x and x square minus yz as it is, this as it is. I'm replacing this R2 by R2 minus R1. So I'm subtracting this row from this row. So 1 minus 1 will be 0. Y minus x is what I'll get. Okay. And now it is this minus this. So this y square minus zx minus this x square minus yz. Okay. At the same time, I also replace R3 by R3 minus R1. Okay. So R3, this is R3, this is R1. So R3 minus R1. So 1 minus 1 is 0. Z minus x here, and here I have z square minus xy minus this term, that is x square minus yz. Okay, so the value of the determinant is the same because I am carrying out this row transformation. Now what I can see is that I have 1, 0, 0. I have x, y minus x, z minus x, x square minus yz. You will see that I have here y square minus x square. So y square minus x square can be written as y minus x into y plus x. That's because a square minus b square, the formula is a minus b into a plus b. And I have here minus zx, minus into minus yz is plus yz. The same way in the third row here I have z square minus x square. Again z square minus x square can be written as z minus x into z plus x minus I have xy here, and I have minus into minus yz plus yz. So let me rewrite it. So I have 1 0 0. I have x, y minus x, z minus x. This I have x square minus yz. Okay. Now here I have y minus x into y plus x, and let me consider take z common from these two terms. So plus z into, I have y and I have minus x, so it is y minus x. The same way in the third row I have z minus x into z plus x, and here I have y common, so I'll take y common, then I have z minus x, z minus x. Now you'll see that in the second row and the third row y minus x is common, so you can say that y minus x is common in this row, and z minus x is common in this row. Okay, so what I'll do is I'll take y minus x common, I'll take z minus x common. What remains inside is 1 0 0, x 1 1, and I have x square minus yz, and here I have y plus z, okay, y plus x, this is what remains, so y plus x plus z here, and here what remains is this z plus x, and plus y. This is what remains. Now you will see that I have y minus x into z minus x. Now if you look at the second row and the third row, I have 0 1, you can read this term as x plus y plus z, and in the third row I have 0 1, again here x plus y plus z. So both these rows are identical, and I have, whenever two rows in a determinant are identical, the determinant is equal to 0. So I get this determinant equal to 0. So I could solve it by using row or column transformation like this. In the previous slide we solved it manually. Okay, so depending on your convenience, whichever you find is easier, you can use any of these methods in finding or solving these determinant equations. Let us consider this example here. So I want to show that this determinant is equal to this. Okay, so again the same way, either you can manually solve it using determinant the way we compute, or you can use row or the column transformations. Let us use row or column transformations here. So this determinant here, let me say this left hand side is D. Okay, so you'll have to look at the elements and then accordingly decide what transformations you'll carry out. So let me replace the column 1. So this is, I have column 1, column 2 and column 3. Column 1, let me replace it by C1 plus C2 plus C3. In that case, what I'll get is this determinant A plus B plus 2C plus A plus B. Okay, so I have 2 A's and 2 B's. So I'll basically have 2A plus all 2 A's, I have 2 B's and 2 C's. So I can directly take 2 common, and I can write like this, 2 into A plus B plus C. The same way when I add this, so C plus B plus C plus 2A plus B, again I'll have 2 C's, I have 2 B's and I have 2 A's already. So again I can say 2A into B plus C, directly taking 2 common. The same way when I add these columns, C plus A to this, so I'll get 2 C's, 2 A's and I already have 2 B's. So again 2 into A plus B plus C. Column 2 as it is, so I have A, B plus C plus 2A, and I have B, I have C plus, here I have A, C plus A plus 2B. Okay, so what I can do is, you will see that this is common term in all the all the terms in the first column, so I'll take it out. So 2 into A plus B plus C is common. What remains inside is 1 1 1. I have A, B plus C plus 2A and A here, and I have B and C plus A plus 2B. Okay, let me go to other transformations now. Let me replace R2 by R2 minus R1, and let me replace R3 by R3 minus R1. In that case, what will I get? So that will be equal to 2 into A plus B plus C. The first row as it is 1AB. I'm subtracting R1 from R2, so R2 minus R1. So this minus this, 1 minus 1 will be 0. B plus C plus 2A minus A. So this 1A will cancel. So what I'll have is 1A, 1B, 1C. So I'll have A plus B plus C. Here B minus B will be 0. Then same way I am subtracting R1 from R3. So R1 minus R3. So 1 minus 1 is 0. A minus A is 0. And now C plus A plus 2B minus B. So this 1B will cancel with one of this B here. I'll have A, 1B and 1C. So I'll have A plus B plus C. Next what I'll do is, now you can take A plus B plus C common from this row and A plus B plus C from common from this row. So in that case I'll have 2 into A plus B plus C, okay, and another 2 A plus B plus C that will come out, and one more A plus B plus C that will come out. That will give me A plus B plus C multiplied 3 times, so cube, and inside what will remain is 1 AB. I have 0, this has gone out, so 1 0. I have 0 0 1. Okay, so 2 into A plus B plus C cube. If we compute the value of this determinant, that will come to 1, and that's exactly what we are trying to show. So we have used column transformations here and row transformations to show that this determinant is equal to this. This could also be, of course, be solved manually, and you can try it to show that this determinant is equal to this.